All right, can everyone hear me? Thumbs up. All right, cool. My name's Ty. Let's get this started. If my clicker would work. There we go. OK, cool. When Uber was a really young company, there was just a small group of engineers on the mobile team. And they could easily communicate with each other and share tribal knowledge. And that team built a single app that was in one repo. And they could use Ant and Eclipse, the simple tools at the time, to build that. And that app was a really small app with a tight focus. It was a really good MVP. And that team quickly grew with the business, going from one Android team to multiple teams, including a platform team and multiple vertical teams built on top of that. The team thought it was important to address the scale, so they standardized around MVC architecture and used modern tooling for the time. These components were very well composed, and they allowed for new engineers to develop against the solid principles. And over time, that one app became multiple apps across different repos. And common code was extracted to create a library that both the apps could depend on. And that common code was modularized into multiple core library repos that were consumed as versioned Maven dependencies. And with the new contributors and a good foundation, they could scale and launch new product offerings. And that organic growth became massive, with literally hundreds of mobile engineers contributing to a small number of apps. And new pain points emerged that were unheard of in the industry. Tribal knowledge fell short, communication broke down, and developer productivity slowed to a crawl. Many more controllers were added to the architecture. And this caused bottlenecks to emerge, where certain areas would become bloated with scoped objects on the graph. They'd be coupled to more downstream dependencies, creating a large number of unmaintainable classes. And the iteration process slowed, requiring updates to downstream dependencies, multiple sequential CI jobs, and then updates in multiple top-level apps that were consuming those dependencies. Developer productivity took a huge hit, and architectural silos emerged throughout the company. And the product choices continue to follow the organic growth model, essentially creating a kitchen sink of products for the end user, with little focus on usability. The number of product choices in the bottom sheet of our application became a joke to many people. And at this point in 2016, we knew that growth couldn't be allowed to continue unchecked, and that scale had to be planned for. And so at this crossroads, we decided to rewrite and redesign the Writer app at the same time to create a product that could be built upon for years more to come at the scale that we'd been growing at. And this talk today is going to cover how we took a step back to approach opinionated scaling, the tools and processes that we've used and open sourced, and that these will help you prepare to focus on scale for your own app, hopefully without over-engineering. So today, I want to walk through a few major areas of scale that we've made headway against. First, we'll discuss our project structure and build needs. And then we'll talk about RIBs, our custom architecture solution and the backbone of our modern applications. And then I'll finally discuss some of the libraries and tools that we use to facilitate faster mobile development at Uber. This will in no way be an exhaustive list, or I'd be here all day. Instead, I'm going to give a crash course of a few of these, and then I'll link additional resources at the end so that you can dive into the ones that you think might make sense for your projects. I'm also not recommending explicitly that you use all of these or any of these specifically. Be thoughtful in what your own scaling needs are. Many of these are designed for bigger apps. So be careful not to over-engineer. You may have noticed in my first slides, as I was kind of giving that history, that we more or less started in a monorepo, and then we split it out into a multi-repo structure with multiple apps and different libraries. Like many other companies at this scale, Google, Facebook, we started having to think about what a monorepo might look like. We considered the trade-offs of the mini-repo model to the monorepo model. Many of the developer productivity issues that we had been facing could be pointed directly at some of the issues dealing across multiple repositories. The three major pain points that we were feeling were issues with transitive dependencies, updates being required in multiple repos, and duplication of efforts. The emergence of multiple types of architecture and conflicts amongst different projects as teams worked in more isolation. and long build times, as the build system was inefficient at parsing and building a sub-modularized code base. To demonstrate a problem in the multi-repo world, let's assume we have an app with a chain of transitive dependencies. And if an API breaking chain is made at the bottom of the chain, each one of the apps that are consuming that will need to make an update for that. So you'll make it in the app itself. You'll send it out for code review. CI will run, deploy it up to your internal Artifactory instance. Then you need to go to the next library up in the chain and update the dependency to that version, commit that, send that to master, let that deploy to Maven, and do that again for the third and the fourth until you're finally in your app. You can see how that is very inefficient. And that's one of the best case scenarios, where it's updated properly. A more common scenario in my mind is when we have a build script for an app in a library that the app uses, and you'll start to notice here some issues. Right here, we're declaring some fundamental libraries like storage and networking. But if you start to look at the transitive library, you'll see that the versions are mismatched. Now, Gradle will resolve to the highest one by default unless you specify another conflict resolution strategy. But this could be disastrous for runtime crashes, where you had a specific library that was expecting one version of a transitive dependency that it had, and your app declared a higher version, and that caused some sort of issue. And so these pain points, among many others, drove our decision to move from a series of multiple repos to one large mono repo per platform, iOS and Android. And this new project layout gives us the ability to update across multiple modules in one commit and really increase developer productivity. For example, here would be a similar example to the mini repo problem that I gave a moment ago. But here, we can guarantee that all of our downstream libraries are pointing to the same version. So one commit to this will be reflected everywhere. And in addition to the project structure, to maximize the gains for our developers, our developer experience team has invested heavily in converting our primary build system to be driven from Gradle to Buck. Now, while Gradle has made tremendous gains in terms of performance and features with modularized code bases, at our scale of 1,000 plus modules in our monorepo, Buck gives us better performance and fine-tuning. If you're not familiar with Buck, it was built by Facebook. And it follows a similar architecture to Bazel, Google's monorepo build system. Its build architecture is based on cacheable outputs. And Buck encourages many small modules, and it's very parallelizable. It will really use all the cores on your CPU. If I start a build, I have a hard time even streaming music on my computer. It'll start stuttering. Because it's so parallelizable, it can cache these outputs of the small modules. So it makes it very fast. And if you use advanced features that it provides, like the network cache, it gets even faster, because if any of the other developers in your team builds that, you can take advantage of it. Buck also has great IntelliJ integration, keeping a productive workflow, including concepts like building from the IDE, deploying, running tests, using unloaded modules for really large projects like monorepos by creating IML files for the specific modules that you may need to index. Buck is a lot more focused than Gradle, making it possible to attain much greater speeds under certain scenarios. But it makes it less flexible overall. It's also notoriously more obnoxious to configure the build scripts. And you need to have one of these build scripts per module. Because of this, I like to say that Buck is like rocket skates. You're going to go really fast, but you don't want to change direction or fall down. To address this hard-to-configure script problem and the lack of features that we did enjoy from Gradle, I'm going to, like dependency management, I present to you one of our open source projects called OKBuck. Adding OKBuck to your Gradle project is trivial and follows the standard Gradle pattern. And then you can execute a Gradle task to configure a Buck wrapper object. This will configure your project and create Buck config scripts per module, eliminating the need to write those nasty scripts yourself. Running the Buck wrapper also has multiple advantages, as opposed to running Buck directly as a binary on your system. It downloads, installs, and updates Buck. It has minimal overhead to decide when to run OKBuck before involving Buck if you're using Watchman, which is watching for changed files. And it also handles gracefully the cases when OKBuck may fail or is abruptly stopped or the daemon is killed. Now, the speed of Buck is in a hyper-modularized code base, with the simplicity and features of Gradle, like dependency management, seem like the best of both worlds. And this is how we're currently building our monorepo. Another awesome feature when using the Buck build system is a tool that Facebook provides called Exopackage for development builds. Exopackage constructs a shell application where each module's dex file can be hot swapped out. Now what this does is it allows for much smaller changes to be deployed to the device, similar to Instant Run. Here on the first run of compile and install to the device, the APK builder will construct an entire shell of the application and all the dex files, and then deliver that to the device. So you're going to get a long install time. But on subsequent compiles and installs, it's only going to send the changed dex files over to the device. Now, with a really large app like ours, that can make the difference in 30 seconds for install time. So it's pretty significant for local iteration. The last helpful build tool that I want to cover is also a problem that I'm sure most of you have experienced at some point. But as you get more developers contributing to your code base, you're going to run into it more often, and that's when master's broken. People step on each other's toes, and merge conflicts will happen, especially as you're getting more contributions. Even if CI is passed for a specific job, when that developer goes to land, another developer might be landing at the same time, and a conflict may happen on master that wasn't prevalent in one of those CI jobs. With hundreds of mobile engineers, we were running into a state last year where we were having master be broken multiple times per day. Developers would get pulled, rebase their change, only to see it start breaking. Build times were slow. They aren't immediately sure if it's their feature that's causing the break, or if it's someone else's. And there's a lot of commits that they have to look through to figure that out. So productivity plummeted. So we introduced a concept that's not original called the submit queue. And this gives us the power to validate that a diff will merge successfully against master by rebasing it automatically and running a series of automated checks that you can define. Keeping master green is crucial to keeping developers' productivity up. So this technique has been implemented by numerous open source communities. If you're looking to do something similar for your own company, I'd recommend looking at the Kubernetes project, because they have an open source submit queue and merge bot that's pretty unique and demonstrates a lot of these concepts. With our project structure defined, compiling and sailing smoothly, I think it's time to move on into how we're actually building the applications. So in early 2016, a focus group of engineers at the company were charged with researching and creating an architecture and platform that would allow, for mobile development, that would allow it to scale along with our growth for the next few years. They researched many of the existing architectures and frameworks that existed at the time. And we codenamed our own architecture Presidio. You may hear that reference a little bit later. And it would become the foundation of what many of our modern apps are today. And there were a number of goals that were stated at the beginning of this project, high-level goals. We want to be able to define the difference between core code to the application that's critical to the user and optional features that, if they're crashing, could be turned off. With scale only expected to increase, we want to set up a foundation for the app that will last us years. We can't afford to do another rewrite or re-architecture another year, and then another year again, and then another year again. We want to create guidelines and rails for developers and designers to work on, allowing fast, consistent, and reusable features across many applications. And you can't define success without proper measurement. And it shouldn't be left up to the individual teams or developers to figure out how to measure application-wide metrics. So our foundation should provide that as a first-class citizen to these different teams that are depending on it. Users rely on our application as a daily utility critical to their lives. People use it to commute. People use it in emergency situations. And to move fast as a company, people can't be afraid of breaking the application under these scenarios. So this foundation needs to provide a basis for experimentation by teams that want to push the envelope without worrying about it. Lastly, our tools should empower, not inhibit, a great app experience. It should be performant, handle things like degradation for low-end devices out of the box. So based on these architectural goals, we investigated many well-established architectures that were on the market, like MVC, MVVM, Viper. And we found each had downsides in our use case. MVC and MVVM commonly had hard-to-maintain fat view controllers. Our old writer app was built using MVC, and this is something we ran into. We had a ride request class that started as 300 lines of very focused code. And by the time that we finished this rewrite, it was many thousands of lines of code. It was very unmaintainable and very fragile, very hard to test. And updates slowed down. We also loved a lot of things about Viper, including the much more explicit separation of concerns and easier testability. However, using a pure implementation of Viper would require us to couple the application state to the view tree. And that, in our mind, would leak business logic through the presenter. So based on the principles that we had and the inspiration from Viper, we created and open sourced a cross-platform architecture pattern and 2 sets of natively implemented frameworks called RIBs. It's implemented natively on Android and iOS, but the domain language can be shared between the two so that you can have your entire mobile team collaborating and having the same language to talk about their architecture choices. So what is a RIB? A RIB unit is defined by a builder, which creates the other components in the architecture of the RIB, an interactor to manage business logic, and a router to help with routing between different RIBs. And since we wanted the application to be tied, we wanted the application state tree to be tied to business logic as opposed to being tied to the view tree, it encompasses an optional view and an optional presenter to manage the data model translations, layouts, animations, view inflations, that sort of thing. So our writer application is represented by business logic state trees, where each node is a RIB unit here. Each one of these will only be instantiated, attached, and active when it's needed based on the user's behavior. So let's walk through what an active RIB tree might look like while the user's requesting a ride. Initially, when the user launches the app, only the RIBs related to the home screen will be active. They're inflated, they're on the screen, they're in memory. Everything else is currently detached, not instantiated. As the user moves through the car request flow, confirming their ride, the home RIBs are detached, and a confirmation RIB is attached in its stead. Followed by a refinement choice, where the user can refine the location to make sure they're picked up in the right spot. And finally, all pre-trip related RIBs are detached, and an on-trip branch is created and attached. Communication between RIBs was designed to satisfy the open-closed principle. For communication downward, we rely heavily on Rx. A stream is placed on our DI graph by a parent RIB, and then an emission is made on the stream so that the child RIB can subscribe to that and get the information. And for communication upwards, the child RIB would define an interface that the parent would implement, and then the child would execute that method as a callback. With the backbone of our application defined, I want to walk you through some of the tooling that we use to both support RIBs, as well as generally empower better mobile development at our company, especially at the scale. To assist developers in creating RIBs, one of the major problems that we heard was that there was too much boilerplate. And so we've created an IntelliJ plugin that's open source in the RIBs repo. By the way, the links for all of these repos that I'm talking about are going to usually be at the bottom of the slides. And so this IntelliJ plugin will allow you to bootstrap up a RIB unit. It'll create the interactor, the builder, the presenter, the view, the router, as well as the Dagger components that the builder is encapsulating, so that you can easily wire those up to hand dependencies around your RIB tree. One of the most important pieces of functionality that was built into the new writer and driver apps architecture is the ability to distinguish between core code that the user requires to complete a trip and optional code backed by a plugin system, so that we can enable safe rails for developers to build and iterate, but we can turn those off remotely if it starts crashing the application or inhibiting the user's experience. So we recently, by recently I mean last week, open sourced a meta generation tool called Crumb. And it's the backbone of this type of functionality. Crumb enables you to generate metadata in downstream dependencies that are consumed in the parent app. They act as providers of information. So the upstream parents will consume that, thus the breadcrumbing idea. So we combine this with tools like Java Poet or Kotlin Poet to generate code based on this metadata that could be useful for this concept, and I'll dig into it a little bit more. Here's a diagram taken from the Crumb repo. And this is showing an example plugin system. And in our example here, we're demonstrating a dictionary. Perhaps you have different languages, and those are described in separate modules. And you want to automatically collect those as a plugin system and then generate code that would use those all at once. Now, clearly, you could do something with reflection or things like auto service, but oftentimes those are going to have performance hits. This allows you to do that sort of automatic plugin detection and code generation on both sides. So it's pretty cool. And in the Crumb repo, you can see the full example of a sample plugin system that we built. So feel free to reference that later. In our applications, however, we've built a more complex version of the example plugin system from Crumb on top of our internal A/B testing backend service. This allows us to roll out new features behind a plugin. And in the event of a crash or outage, we can turn that off on the server, and it'll be disabled for the end user. Here's your typical plugin. It contains an identifier that can be referenced against a copy of enabled experiments, as well as information to determine if it's applicable for the dependencies that are provided. And we then need to create what we call a plugin point class. And it lists all the plugins that adhere to that interface with a common dependency. In this example, we just have foo plugin factory. You could imagine a scenario where we have one plugin point that's handling, for example, all deep link types that are coming in. And this would list all registered deep link handlers. And then the previous implementation would describe if the specific plugin could handle it or not. Finally, we're able to utilize that plugin point to request a specific plugin and then act against its API if it's returned. In this version, I've added a generic A/B testing framework as the parameter that we're passing in to construct the plugin point, to kind of give you an example of how you might think about doing that in your own code base. And then since the get plugin is, it could be null, coming from the Java interop, and we may not have a plugin that can handle the specific dependency, we need to have that as a nullable var here in Kotlin. Then only call the do work, which is the implemented interface, if we got that back from the plugin point. Another area that can be challenging when dealing with dynamic app state is how to reference a static snapshot of the tree, right? So you have things like a deep link that comes in, where you have this serialized static reference to a state of the application that needs to be attained. But you had this very dynamic rib tree where everything in the node, as a parent node, was understanding how to configure the child node. So that gets pretty complex. And so to address that, we designed a framework that interops with ribs called workflows. And this is additionally available for you now. And it's a framework to describe reactive steps in a rib tree. The workflow framework is composed of 3 parts. The first is a step, which is just a single action to be completed. The second is an actionable item, and it's an interface representing the steps a specific rib can accomplish. And the last is the workflow class itself. And this describes the series of steps required to achieve its goal. So here's an example of example diagram of a workflow handling a single sign-on deep link into the Uber app. Once the plugin point creates a specific workflow to handle the deep link that's coming in, it will describe the number of steps that it needs to use to accomplish navigating the rib tree. Now, each one of these interactors in the rib tree are going to implement an actionable item interface that's going to describe the steps. And so if we started at the root of our tree, we could potentially wait until the user signed in, and once they have, we would move on to maybe navigating to the next node in the tree. And finally, we would show a full screen that has the information around single sign-on so that the user can do the thing that they were trying to do. So here's the code to handle the meat of that workflow. We have a series of steps defined that will walk from root down to our main interactor before attaching a full screen rib. And you can see most of these here in this getSteps method. For example, in our root interactor, we define a step that waits until the user is signed in, and then it triggers the next step. So if the user was already signed in, if their app had previously finished that flow, when the user activated that deep link, it would immediately return. Under the hood, this is just using Rx, so it would just signal, and it would jump to the next reactive step in the workflow. But if the user needed to walk through the sign-in flow, then this is going to be paused, and it's going to be waiting for an emission to the stream. And once the user's finished that sign-in flow, and the proper rib attachment has been done, this will emit, and then the deep link workflow will continue. So we've covered ribs and a variety of tools to help make them a bit more usable and understandable. So let's move on to tools that aren't as directly related to ribs that we use to scale. As Android apps grow, providing common features and consistency across UI elements becomes really challenging. You have a lot of teams that don't necessarily always get the same information. Sometimes it's hard to discover. Sometimes they're just not aware of what to be done, what they should be doing. But for the user, it's important that they have a very consistent look and feel for their application. And so to keep consistency for the user, we collaborated with our designers to create a style guide for downstream teams. We also call them program teams. And they consume this directly, so their designers can reference this, their teams can reference this, and they know what they should be using in the application. And this solved one part of our problem, but it introduces two more in my mind. One, since Android owns the views that are implemented in the framework, those base classes, it often becomes an unmaintainable mess when you have common logic that you need to apply to all your base views. For example, we have base classes for all of the Android views to handle things like the RX binding APIs, automatic analytics, adding accessibility helpers, things like that. And so that gets really problematic if you had a team that was just implementing the same thing in all these base views that you didn't have control over. And then the other problem in my mind is that as an organization grows, what ensures that the downstream teams are actually using the appropriate things? Even giving them all this information, it's still noisy in a big organization. How do we know that they have the right, that they are creating the right user interfaces? So to address the first point, we built and released a tool called Artist. Artist is a Kotlin-based code-generating tool that allows you to generate a base set of Android views in your application. So its views are created using a stencil and a trait system. Each view type is declared with a single stencil, which is comprised of a set of traits. And all of this comes together to create an easily maintainable system of stencils and traits. The stencil describes the view to be generated, and it has properties that can be configured. And a trait has a hook into the stencil's code gen, where you can implement specific pieces of functionality that can be shared across multiple stencils. Here's a basic example for a trait. Here we want to create a convenience method for checking the visibility states of a view. So we'll iterate through the visible states here, visible, invisible, and gone. And for each one of these, we're going to create a method that we want to code gen onto the appropriate view for that specific piece of visibility. So is visible, is invisible, is gone. Next, we'll write up a stencil that specifies the view information to be generated, as well as listing the traits that were added. So in this example, we're creating a switch. And that switch will now include the trait that we just described for the visibility helper methods. And so that ends up generating something that looks like this. We have a switch, foo switch, that extends switch compat from the app support libraries. And it has our methods, is visible, is gone, is invisible. So if you want more information about Artist, check out the repo. It's easy to integrate with your Gradle script, and it's easy to get started in using. But we still have that second problem that I mentioned, where usage in the organization, what guarantees people are using these generated views? Well, we make extensive use of lint rules to give developers immediate feedback on inappropriate uses or potential errors. So here we have a simple lint that extends the resource XML detector. And when this discovers usage of the standard switch compat, it'll throw an error to the developer informing them that they should be using our foo switch instead. Secondly, we automatically add blocking reviewers in our code review process through a tool called Herald, which is part of the Fabricator code review suite. It's an open source code review tool that was originally built by Facebook. Herald's a powerful part of our toolchain because as a team grows, it gives us important information to be notified when a team is making changes to something that may alert a different team. In addition to the errors I mentioned, there are a slew of others that will impact large software projects more often than smaller software projects. The larger the project grows, the more likely you're going to be affected by things like uncaught null pointer exceptions, for example, the infamous billion-dollar mistake. One tool that we use on multiple projects at Uber is error-prone, a fast compiler plugin built by Google that will fail at build time instead of doing static analysis after, with common errors. And it has an easy-to-write checker plugin system. For example, in this piece of code here, we're injecting the object graph after we've called super.onCreate. Now, this might seem innocuous, but this can cause configuration issues where the system attaches fragments before you may have the chance to do something, or reattaches fragments, I may say. And if those go and try to access your graph, you may have state issues. So error-prone will halt execution at build time to let you know about the error and resolve it. And error-prone, like I mentioned, is a plugin-based system where you can write additional checkers. And that's what we've done. When we looked at Kotlin and Swift, one of the things we really liked was the nullability stance that the languages take, how it throws it in your face at compile time. And we wrote null away to do that in Java. This takes the famous billion-dollar mistake and fails it in a very similar way to how Kotlin does. And it's fast. It can run on every build of your application with little overhead. With a quick example, we have a method that takes x, and it prints it out. Now, in this case, we are sending null. By default, null away assumes all annotated parameters are non-null. Now, at build time, null away will alert us to this issue. And then we can fix the issue by adding an annotation for nullable, but x is still null, right? And so when we called x.toString, that would crash. And null away would tell us that as well. So here we also need to do a null check. And with this in place, null away will now proceed. At Uber, we combine error-prone with another validation tool that we've created called RAVE, which stands for Runtime Annotation Validation Engine. RAVE uses the annotations already present on your data models to do code generation to create validators that you can use on dynamic data to ensure that it adheres to the contract that you expect. So first, if we wanted to use it, we would create a validator factory. So here's a simple sample factory. And you need to create one of these per module. And let's assume we have a model that's being created from JSON from a network request. Now, we, in this case, have non-null annotated on the get match. But since this is JSON, there's a potential that the server could be handing us a null value instead. And we wouldn't know that. Our code is programmed to handle this as non-null. And so this could cause a crash in the application. But by using RAVE with this previous validated factory annotation that is on the screen, we now code gen a validator that understands how to handle this model. So it's not using reflection. It's very fast. And we can now put this in our code and have it throw an exception when there is an issue with the data that we got back from the server. So this, for example, would be really easy to throw into a retrofit adapter that could efficiently validate models on deserialization. Now, while RAVE is really powerful, and we use it when we have dynamic data, I would highly recommend taking a slightly different approach for your networking models and your API requests when possible. Use a tool like protobuf or Thrift to have the same generated model that lives both in your client and on the server. And that'll guarantee states and have much more efficient networking traffic using a binary protocol. These tools typically allow you to define a language-agnostic spec and then generate class files for various code bases. For most of our main models and services now, this is what we use. We use Thrifty. It's a Microsoft-backed Thrift generation tool, similar to Wire. If you're familiar with Wire, it's Square's implementation for protobuf, which generates a much more efficient mobile-focused model file from protobuf IDLs. Thrifty does similar for Thrift. Wow. My notes are there. Cool. I'll fix that before I post these. So I'm also posting some resources here. These are going to allow you to dive deeper into the different topics that I've covered today. These are should just be a starting point. Hopefully, this is just a crash course and things that could help you out. Most of my colleagues have produced these other content, and I would highly recommend them. Thanks for attending today. I hope these provide some pointers for you to think about with scaling. If this sort of work interests you, we're definitely hiring at Uber. Come talk to me. And I'll be available to take some questions after if you come see me in person. Thank you.